All right, so in this video, we're going to look at 30-year fixed rate mortgage rates and 10-year, the 10-year Treasury. So we're going to need to import NumPy. So let's import NumPy as NP. Let me zoom in a little bit. Import NumPy as NP, import pandas as PD. Let's import date, time. I don't think we'll need it, but all right. So let's import pandas data reader. This is how we're going to get our data. So we're not going to use we don't have a CSV file or anything like that. We're just going to use take it directly from the Federal Reserve's website. And let's from stats models. Let's import. Let's think about what all we need. Let's import from stats models dot TSA or from stats models dot time series analysis. Let's import our AR model. So as well, we're gonna try to make a autoregressive model to fit the data, and then from stats models dot time series analysis, let's import stat tools, and let's from stats models dot time series analysis. I'm sorry. Dot graphics, not time series analysis, or not TSA. From graphics, import TSA plots. So this will let's do a little bit more, and then let's do matplotlib inline. This is so the matplot graphs and plots can show in Jupyter Notebook. So this should be everything we need. So now let's do our symbols. So for the symbols, let's do mortgage 30 US, which is the 30-year fixed rate mortgage. And let's do DGS10, which is going to be the 10-year Treasury. For our start date is equal to date, time, date. So for a date, time, date, it's the year, month, and the day. So let's do 2005, January 1st, let's do our end date. And let's set our end date to 2015, December 31st. So this isn't going to be exact. We're going to be looking at weekly data, but this will be able to get it for us. Now let's, because we're getting two separate time series, let's do data.pd data frame. Then we'll say 4 SN symbols. So we're going to do mortgage 30 US first, and then we're going to do DGS 10. I believe the mortgage 30 US is every Thursday, and it's weekly, and I believe DGS 10 may be daily. I might be wrong, but I believe mortgage 30 US is going to be less frequent, or have a lower frequency than the 10-year Treasury. So let's do the so let's do the mortgage first. So let's say data column S. We'll create a new column S. Then we're going to use the data reader. So WB dot data reader. Say the name. It's going to be equal to yes or S symbol. So we're going to get the mortgage 30 US. We're going to go through this loop. Then we're going to start the loop again, and we're going to use S is going to be equal to DGS10. And our data source is going to be equal to Fred. Remember, it's case sensitive. Our start is going to be our start date variable we create up there. Our end is going to be the end date. End date. We specifically want the S column. That way it doesn't restart or try to do anything weird. So this should be able to get us our data. Make sure it worked. Let's look at the first few rows, and it did. And the reason why we wanted the less frequent series first, the less frequent time series first, is so that whenever with that, it will create the index, and it will match those days with that specific day for the Treasury. So when the index doesn't match, it just won't go in. So now let's create a new column. We'll name it spread. And this is going to be equal to the mortgage rate minus, it's going to be spread between the two. The mortgage rate is going to be higher minus DGS. So now we have the spread. And remember, for stats models, it can't do anything if there's nans. So let's drop all our nans, or not in numbers. Set that to be in place. Now let's look at let's see what the spread looks like. So we'll plot it. Notice that it's never less than 1, or I'm sorry, never less than 0. If it was less than 0, that would mean that the 10-year Treasury rate is greater than the mortgage rate, and that's that would be unlikely. It looks like here it was close, so there was almost only 1% difference between the two rates. So we want to try to build an AR model on this. So let's use the augmented Dickey-Fuller test that we went over before to see if it will work. So we did AD Fuller. AD Fuller, the augmented Dickey-Fuller, is going to come out of stats tools. So stat tools. So our results are going to be equal to stat tools dot AD Fuller, and we're going to give it our Y. The Y is going to be the spread. It's going to be a series, and we'll look at the results. So we can see that given a, let's just do a 5% significance level, that we can reject the null hypothesis and there is not a unit root. So let's actually print this off, or let's show it a little bit cleaner. We'll print, so the ADF statistic, and this time we'll do it a little bit differently. We can do the two curly bracket and say format, and close it in there with the first value. Either one will work. This is a little bit different than how we did it before. But if we do it like this, you'll still see the same thing. So there's lots of different ways to do the same thing in Python, as there is in most programming packages, most languages. So in the last video, we did the %F for our formatting. This one, we're doing the curly brackets, but they'll both do the same thing. So now we'll look at this. So now we have our ADF statistic, which is -3, and we have our p-value. So given a 5% significance level, we can reject the null hypothesis, and there is no unit root. So let's look at a autocorrelation plot. So let's plot _ACF, and let's give it our just to make this simple, just to make this a little bit simpler, I'm going to say Y is equal to data spread. And now we'll be able to just look at Y. So this is 600 lags. That's pretty aggressive. We don't need that many. Let's just look at the 50 lags. Let's look at the first 50. So you can see that it is weekly dependent. It is weekly dependent, or yeah, weekly. It's weak. But over time, as the number of lags get large, as K gets large, the correlation between the lags gets small. So this is still stationary. So let's actually do a AR model. So the first one, let's do no max lag. So let's set, let's do model. We're going to do AR model. So MDL for model, AR model, and we're going to do AR. If I do tab, you can see all the different things we can do. We want AR. We're going to give it Y. We're going to fit. So let's do this, and then on the model, we can get the parameters. So we can do params. Let's round to the 4 decimal places. So we do this, and it gives us 19 lags. So if you don't tell the computer a specific number of lags, it will just continue to do it. So this gives us 19 lags, so 19 weeks, 19 weeks, which is pretty large. Let's change it. Let's do a max lag. Default will be max lag equal none. Let's do max lag equal 3. So now it only gives us 3 lags. So we have a constant, then beta 1, beta 2, and beta 3. Default would be none, and then computer chooses 19 for the best model. So let's look at what both would give us. Let's see what both would give us. Let's plot it. Let's say y is going to be our actual value for y, and let's say y hat is going to be our estimated value, our predicted value. So let's do model.predict. This is all built into stats models. So we have MDL for model. So model.predict is going to be our predicted values for the spread between mortgage rates and 10-year Treasury. And let's create a blank figure, fig size of 8 by 6, just so it's a little clean. And let's plot it. Let's plot the y, which is going to be the actual value. Then let's plot y hat. They both have the same index, and this is going to be the estimated value. And then let's turn on the legend so we can tell which is which. T is not defined. Looks like we forgot to import matplotlib, which is okay. Let's import matplotlib.pyplot as PLT. Now it will work. Now they're saying there's some must have first dimension. So we're saying that they're a little off. They're still saying that they are a little off. X and Y must have the same first dimensions. Okay, I know what's going on here. So let's say Y is equal to Y dot drop in A, just so it drops that value. And now this shouldn't be a problem. So it looks like we're having a problem here. Let's do y hat index. Now it fits. Okay. So that was my fault. So it's good we had that error. It's good we saw it, because y hat is a lag. There's a lag between y hat and y. So that would mean that this is 19. So that means that it's missing the first 19 values. So that was the mistake. So we can see the estimated value versus the actual, and it's pretty closely fit, but you don't want to overfit the model either if you're going for it. So let's lower it. Let's say let's do 5. I just arbitrarily chose 5. You see that it's still good fit. Maybe you can see that as it gets to 19, that gets into the lower correlations. So let's do 3, just because. And it's still not an awful fit, but it loses some accuracy. And then to kind of look at, let's do our let's look at the first expected. Let's look at the first moment. Let's look at our expected value for the spread. So this will be our last thing we do in this video. If you look at the model or the model parameters, so all the lags, remember back in one of the previous videos, to find the expected value, you get the constant divided by 1 minus the sum of all of the other coefficients. So beta 1 all the way to the last value. We'll sum it up, and this will give us our expected spread. So if you just ran this model, if you just ran that predicted value, it should yield to 1.74. And a way to kind of see how far that is from the mean, we can just do y dot mean, and this gives us 1.73 just about. So on average, 30-year mortgage rates are about 1.73% higher than the 10-year Treasury. So this is it for the for this video. So we so in this video we created a AR model, an autoregressive model to model and predict the spread, or to model the spread between the 30-year fixed rate mortgage rate and the 10-year Treasury yield. So that's it for this video. In the next videos, or the next set of videos, we will talk about the stock to flow and using scarcity to model Bitcoin prices, or to value Bitcoin.